Okay, suppose that I give you two vectors, let's say a and b. Sorry, let's draw the x and y plane first. So let us have a going this way and then b going this way. And now let's say that I draw the same vector here going this way and then the vector a, and assume that they're all parallel. So this one is parallel to that one and they have the same length. So this one here would be b and this one would be a. And suppose that I tell you to find the area that is the area of that parallelogram. How would you actually go about finding that area? Well, it turns out there's a really interesting property of the cross product of two vectors that says that the area of a parallelogram defined this way is actually just the magnitude of the cross product. So it turns out that this cross product we calculate, it gives us a vector. In this case, the vector would be perpendicular to both a and b, which means that this vector would go along the z-axis. So if I draw it as n, then the magnitude of that vector, which would be its own length, would also correspond to the area of this parallelogram. And I find that this is a really interesting property, because how can a length be equal to an area? I mean, that's a very counterintuitive kind of concept. And if you consider it from the point of view of units, it doesn't make sense, because this would have units of length and this would have units of area. But it turns out that if you consider this on a dimensionless basis, then it does actually correspond to the same quantity. So just to show you how that works, suppose that I give you two vectors. So let's say I give you the vector 1, 2, and the vector, say, 3, -1. Now, if I tell you find the area enclosed by these two, first of all, we need to know how they look on the xy plane. So we're gonna draw this one. This is going to be 1 and 2 here. So that will be vector A. And now I'm going to draw vector B. So that's gonna be 3 here along the x-axis and -1. So we're gonna have -1 here. So this is vector B. And now if we project these two, so I'm gonna draw this in a different color here so you can see it better. If I draw two vectors, so one going in this way and then one going in this way, then the total area that is enclosed by those two, the total area here, is going to be given by the magnitude of the cross product between the two. So first of all, let's define the cross product as coming in out along the z-axis. So if this is the z-axis, this would be the cross product of those two. So basically, we will define n as being the cross product of A with B. Now you might be thinking, can you actually define a cross product in two dimensions? Because originally in the last video, when we defined the cross product, we said it was a 3x3 determinant. So we said it was I, J, and K. And then we had A1, A2, A3. But it turns out, yes, we can, because these vectors, we can express them in the three-dimensional space by simply noting that they have no component along this z direction. So essentially, these vectors exist in 3 dimensions, but actually they exist in any number of dimensions, but every other element is just going to be 0. So we don't actually see the effect that has on the whole space. So in this case, if we do A cross B, we will have 1, 2, and 0. And then for B, we're going to have 3, -1, and 0. And as it turns out, this is going to give us the following. Remember, we're going to do the cross multiplication, so I'm just going to write it down here. We're going to start with the ith component. Well, this times that minus this times that, that's just 0. Then the jth component, which is going to be this times that minus this times that, so that's also 0. And we're going to have the kth component, so now we have 1 minus 1, that's -1. Minus 2 times 3, so that's -6. And in the end, we get -7k. Or we can also express it in the form 0, 0, -7. So we notice immediately that because there's this negative sign, the vector is actually going to be pointing along the negative z direction, so it would go out into the page in this fashion. Okay, that's all good. Now if we calculate, okay, so let's say we calculate the length of this vector, well, we know it's just going to be 7 because we're going to square the components and then add them together. There's only one non-zero component here, so this goes out with that. And of course, remember, we're also squaring the 1 here, so that becomes a 7. So this is the total length of the cross product. And in essence, this would also correspond to the area. So the area of this parallelogram would just be A cross B. Now, is there any way that we can prove this is the case? Because even I am a bit skeptical about this right now. I mean, how can it be that this length of this vector is equal to this area? Is there any other way we can show this? Well, we can use some simple geometry to show that that is the case. So what I'm going to do is I'm going to move up here. So let me just erase this here. And I accidentally erased my A, so A is 1 and 2. Okay, so what I'm going to do is very simple. I'm just going to break this down into components. So essentially what I want to do is I'm going to have my XY plane here, so X and Y. I'm going to have my vector 2 here, but instead of drawing a vector, I'm just going to draw a line. So this is 1, this is 2. And now I'm going to draw the line that corresponds to B, so this will be 3 minus 1. And then we know that we're just going to repeat this process. So we're just going to draw another line here. And we can also, so it's very simple if we look at the fact that we're going down by this much. So this vector here, vector B, it goes down by -1 every 3 units. So if we're starting off at 1, then we're going to end up at 4 here. But if we're starting at 2 on the y-axis, then that means that we're going to end up at 1. So essentially, our vector is going to go like this. And then we're just showing the other one, and we see that that is basically what we get from that. So now we're going to use simple geometry to find the area of this parallelogram. So what we're going to do first is I'm going to use a rather rudimentary method for this. So basically I'm going to calculate this area first, which is also going to give me the area here. So basically this area here, because if we try to draw this properly, then this area would be equal to that area, and then I'm going to calculate this area here, which is going to be equal to this area here, and then in the end I'm going to calculate this and then add up all the areas. So we know that the area of a triangle is just half of base times height. So we know that the blue area, so I'm just going to draw it here, blue area is going to be the following. We have half of 1 times 2. So this cancels out with that, so that's 1. And obviously we need to multiply this by 2. So that's going to give us an area of 2 because we have 2 blue areas here. Now for the green, we have, let's do the 2 already here. So we have half of the height. So in this case, the height is just going to be 1. And the length is 3. So we have 3 here. Alright, so this cancels out, that's 3. And now we calculate the area here in the orange. So we have orange area. So how many units is this? Well, this is going from 1 to 3. So that's going to be 2. And this is just a rectangle. And then it is going from 0 to 1. So it is enclosed here, so 1. And now what happens when we add all of this together? Well, the total area turns out to be 7 units. So how about that? We'd actually just found the area of this parallelogram by just simply calculating the cross product of these two vectors that actually make it up. And they turn out to be also the length of the vector that is perpendicular to them. So this is just an amazing property, and we can see that the cross product has a really amazing geometric definition, but it is also very useful for defining physical quantities such as torque, moments, and in general anything related to rotation will involve the cross product in some way. So in the next video we will go into some physical examples and applications of the cross product.